I want to now to get into what a normal course would be is plug and chug. I'll tell you some formulas, I'll tell you what steps to do. This is not for Friday. This is for the final. What you're going to be doing for the next 3 weeks is repeating this procedure a million times. So I want to start with a cylinder in a cross flow. All this is in your notes. I'm not going to write on the board for a while now. So is cylinder in cross flow. So now it's not a flat plate anymore. You can try to solve the equations. Yeah, for laminar it's okay, but for turbulent you cannot solve them. So here you have a cylinder, and here you have your flow, right? They didn't put it here. Yeah, here you have U infinity, and then you have like T infinity 2, right? And in the cylinder, now that we talked about laminar and turbulent, you know that if the flow is very slow, it's going to be mostly laminar. If the flow is fast, it's going to be turbulent, right? And so you're going to have a boundary layer. And this boundary layer at the beginning sticks pretty well. And then it gets thicker and thicker until it reaches something that is called the separation point, right? It's related to the pressure gradients. And, but the bottom line is, at some point, this boundary layer breaks and turns into this turbulent wake, right? This is what gives most of the drag in your car, this wake. That's why very often the sports cars like have this kind of fastback, right? So you have minimized this wake. Now, for a cylinder, we're going to talk about average heat transfer coefficient, because when you have a pipe, all you want to know is how much heat I'm putting in or out of this pipe, right? But if you go to the book, you're going to see how interesting it is that different parts of the pipe have different exchange coefficients. So sometimes the pipe might burn or boil or have different behavior here in the front, that here in the top, that here in the back. So people measured cylinders, and they say, okay, the cylinder has this formula for the Nusselt number, right? You see the bar, that means average, right? Plug and chug. So the question is, okay, if I have a cylinder, I need Reynolds, Prandtl, C and M, right? Reynolds, you know how to calculate. Prandtl, depends on the fluid. Done and done. C and M, for C, that depends on Reynolds D. You go to this table here, right? M can be anything here. And look at this. If you have really laminar flows, Reynolds is to the 1/3 here. If you have turbulent flows, right? You see how big this is. They don't talk about a transition to turbulence anymore. They don't tell you, but you know it is there, right? This M that is changing, right, is the M. You see 4/5 here? This is 0.8, right? 4/5 on the board. And look for the very high Reynolds numbers when it's very turbulent. This is 0.8. You see the plate and the cylinder share so many similarities, right? Formulas sometimes get a little bit more sophisticated. So this formula looks more complex, but they attempt to do the same. What you're going to see is that sometimes you have two different formulas to calculate exactly the same, just because, I don't know, maybe the two professors didn't like each other and they told the students to measure the things and have slightly different things. So look, what do we have here? We have C times Reynolds to the M, right? Reynolds to the M times Prandtl to the N. Here we have Prandtl to a 1/3. Now, N, depending on the condition, is 0.36 or 0.37. Oh, big deal, right? Used to be 0.3333. Right, I don't think anybody can measure this so accurately. But anyway, plug and chug. You plug and chug. Now, here's the interesting point of this. For some fluids, especially oil, the oil changes the viscosity very much with temperature. So the Prandtl number changes very much with temperature. So what Prandtl number are you supposed to use? The one on the surface, the one on the fluid, right? So if nobody tells you anything, this is what you do. You take the average between those two. That's called the film temperature. If nobody tells you anything, you take the average surface and fluid, and you go with that. Perfect? No. But it's a good lie, right? Now, these guys say, no, I'm going to do better than that. And they say Prandtl over Prandtl on the surface. So you take all the properties at T infinity. All the properties are for T infinity. But this Prandtl S is on the surface. And this is what accounts for this variation in viscosity with temperature. So for things like air or water, this is not a big deal. For oil, this is an awesome formula. Now, you would say I should use always this. This formula is more accurate than this other formula. But for this formula, you need to have two values of Prandtl. One for the temperature of the fluid, one for the temperature of the surface. You not always have that. Right? Sometimes you do, sometimes you don't. Right? If you do, this is awesome. If you don't, you use this. Right? Are we all on the same page? Because when we talk about viscosity, it's a simple word to say. You go to the book and then you're going to see a table of viscosity. Which one are you supposed to pick? Right? So now you know. In this formula, you would pick the film temperature, that is the average between surface and fluid. And this other formula, you use fluid temperature, except here that is surface. Right? Plug and chug. So this is a methodology we're going to be using forever in this type of convection problems. How to say, but it's very easy to navigate. You say, first of all, what's my geometry? Right? Cylinder, you like cylinder? Okay, you come to cylinder. Oh, you like sphere? Sphere, there you go. Right? So you go to flat plate, right? So, okay, am I dealing with a cylinder? Fine. I go to cylinder. Then you assess Reynolds, Prandtls, as you can, right? So Reynolds, you're going to see in this formula, for example, cylinder says Reynolds of D, right? So you have to calculate Reynolds of D. You have to calculate Prandtl, right? Maybe other factors. Sometimes the formula will say, for this Reynolds, use this other formula. For this other Reynolds, use another formula, right? So you assess that, and based on that formula, you plug and chug, and you get Nusselt. And then based on Nusselt, you calculate H. For a sphere, you have similar regressions. And until we hit the time, I'm going to show you just regression on top of regression, and the story is plug and chug. Don't really care about that because I'm assuming that you can do that on your sleep. What I care is that you know what you do. Reynolds to 1/2, Prandtl to 1/3. Big surprise. I don't know if the book didn't say it or I didn't put it, but you know that is for Prandtl number bigger than 0.7. Right? The 1/3 is the giveaway that they did it for air and water. The Reynolds to the 1/2 is much the same as we had in the flat plate. Right? These themes keep repeating.